Now we have Eli Knaap talking about geosnap, so let's welcome him.
Well, thanks, folks. I'm flattered. This is a packed house. I thought I was talking next door and nobody had shown up, so I appreciate you all being here. I hope I can entertain you a little bit. I'm Eli Knaap. I work at the Center for Open Geospatial Sciences at San Diego State University. Today I'm going to talk about GeoSnap, which is some software that my group at SDSU has been developing for about the last 6 or 7 years or so, and in particular, this is something that Serge and I spend most of our time on. I will mention, by way of getting started, that I really like SciPy. This is one of my favorite conferences that I come to every year. I'm an academic, so this is sort of a change of pace, right? SciPy looks a little bit different than your classic academic conference. And my first SciPy was in 2018, back when we got our first NSF grant to work on GeoSnap. And I gave a talk about what we were thinking and what the software was going to look like, and we were still getting off the ground there. So I'm really pleased to be back here and talk about what it can actually do now. And I will also say that back when I gave that talk, we were still calling this the open source neighborhood analysis package, OSNAP. The problem was when we went to go release that, OSNAP, as you can imagine, was already taken on PyPI, and the maintainer refused to let me have the name. So when I gave this talk and I mentioned this problem, somebody in the crowd afterward raised their hand and said, well, why don't you just call it GeoSnap? And the name has stuck ever since. So SciPy has been incredibly rewarding for our work, if for nothing else than folks who have better marketing materials than I do. So if you would prefer not to listen to me talk, GeoSnap is well documented online. If you are interested in this stuff, I encourage you to go check out the actual software package and its documentation and the paper. So if you feel like tuning me out, GeoSnap is about neighborhoods and understanding places. But there are some unique data concerns and unique challenges and hurdles that you have to overcome to do neighborhood research. And so GeoSnap just tries to reduce that burden and make it easier for folks to do the kind of work that they need to do. So this includes tools for data collection, harmonization, what we think of as interpolation, making sure that your units are consistent from time to time. Lots of different tools for analysis, and then some bespoke visualization tools. So why? If you're in this room, then I assume I don't have to explain to you that neighborhoods matter. This is relatively well trodden ground by now, and I think what I will try and focus, the reason for this conversation is that it doesn't really matter what sector you work in, right? Whether you're an academic or you work in the private sector or the public sector, we think these tools will be useful to you because I have had my thumbs in all of these different worlds. Okay, so here's an article from the New York Times about a year ago where they went and asked folks in New York City to define the extent of their neighborhood. And what is the neighborhood that you live in? Where do these neighborhood boundaries end? And I'm showing this because neighborhoods are something that's sort of relevant in our everyday lives. We can all sort of agree roughly that we live in a neighborhood. We don't always agree on exactly what that neighborhood is or where its spatial extent is. So in this map, we see that some places are really well defined, right? Those colors almost have really sharp boundaries. Other places are really not well defined, right? These colors all bleed together, right? I'm sure we have folks who know New York City much better than I do, so I'm not going to opine here. New York is not a place that I pretend to know particularly well. But so neighborhoods are sort of at once immediately relevant and sort of intangible. And so what do we sort of do about that? Getting a handle on this matters, right? We know that where you live is going to affect who you can become later on in life. It affects the educational attainment that you may achieve, how much you might earn later on in life, the kinds of air and water that we consume, so all sorts of health impacts. So we know that neighborhoods really matter a lot, and this is a very old tradition of trying to study them, right? If you're not familiar with this graphic, this is called Burgess's concentric zones. This is from some sociologists back in the 1920s who took a look at Chicago and realized, well, cities, in particular American cities, tend to be very, very highly segregated along lines of race and class. And that follows a pretty rigid pattern in most places and with respect to the spatial structure of a city. Okay, and so not everyone has millions of dollars to spend sending sociologists out into neighborhoods to ask them about where things are laid out. So how do we sort of automate some of these processes if we think this sort of thing is important? Okay, this matters in the public sector. Here's a graphic from Baltimore's regional plan that I worked on about 10 years ago, where they recognize very explicitly that you need to figure out where things go if you want to give folks in Baltimore a shot. And one of the things that you need to do then is to measure all of the components of neighborhoods that might matter. So this is a massive data collection effort, and this took us years and years to do. If you work in the private sector, they sell these products as data. So here is a tool or a product from Esri that they call Tapestry. Basically what they have done is take a bunch of data at the neighborhood level, throw it into a cluster model, create a typology, and then they sell that typology to their customers, because it turns out that these labels that they assign to a neighborhood are really, really predictive of what people buy and what they do. And so regardless of sort of what hat you're wearing, these are useful tools, whether you want to make a dent in social equity, or you want to make equitable plans, or you want to make money for your company, right? So we need some tools for doing this. We don't always agree on what a neighborhood is. And part of the reason is because of the data sets that we have to use. And so, wait, you said geosnap is an analysis package. Why are you going to waste my time with data? So I'm going to go on a very long digression about why we ended up building a data layer into geosnap. I'm going to use the American context because it's the data that I know the best. Okay, so when we study neighborhoods in social science, I'm an academic, we tend to study the same sorts of things, right? These are demographics. These are things that have to do with the economy, education, the environment, infrastructure, okay? And so all of these things are available, but they require us to write code and go collect them from lots of different places. Okay, so in theory, everything up here, right, economics, education, environment, is all available from the federal government at a nice resolution. So they make APIs available. We could just go in and call the census's API, but there are lots of reasons why that's less than ideal, and I'm going to get into that in just a second. Okay. Alternatively, we can also go to collect data from the National Center for Education Statistics. This provides stuff like the school attendance boundaries that define what school you go to. You can attach this to the data that Stanford has been collecting on standardized achievement to look at what schools are doing better over time. Again, sort of more data munging. The EPA puts out a lovely data set on environmental justice. So this contains things like the amount of ozone or particulate matter or the locations of toxic release sites to make sure that certain communities aren't exposed to toxins more than others. And they want you to use these data. If you want to get a handle on jobs and where jobs are growing and where some sectors are growing, or if some sectors are moving to remote work and what those implications might look like for land use patterns and real estate values, it makes sense to go get job data from LEHD, the Longitudinal Employer Household Dynamics. This is a different census product, so you can't get it from the census API, even though it's from the same folks. And so several different data sets. We all need to use them, but they're all distributed from the federal government by different folks. Okay, so one solution to that problem would be, well, just write a Python API to query the data sets that you need. There are lots of those that are available, okay? So here's SciPy. This was originally written by my colleague Levi Wolf, and this is a package that I contribute to now. This is a self-documenting API for the census. So anytime the census has a new data set, SciPy discovers it, and you can grab it. So this is wonderful, except that when we started to actually do neighborhood analysis and turn our tools loose, it turned out that this really didn't work very well because, number one, we found ourselves writing the same code to query the same variables for 400 different regions of the country, and that's really wasteful and time-consuming. And also there are sort of fundamental limitations in the way that these APIs work. The government is not a rapidly adopting entity, right? And so when you go and query these APIs, what they are doing is traversing either an FTP or an Esri web service. They're collecting either shape files or GeoJSON. They're streaming that back to your box. And all of that is wildly efficient. And it takes a really, really long time. And there's nothing that we can do about that, right? That's the fundamental infrastructure that these services are built upon. I can't do a better API to get that data quickly out of an FTP. But there are much better data formats available, right? So instead of storing data as GeoJSON and as shapefiles, it makes a lot more sense to store them in Parquet and as Apache Arrow. And if you are here at SciPy, then it's probably something that you're familiar with. I'm not the best person to describe to you about modern data formats, but these are much more efficient. They're much, much, much smaller, especially for spatial data, and extremely performant. So what we decided in Geosnap was that instead of writing middleware to query these data sets, most of them are not really rapidly paced, right? They come out maybe once a year, at most twice a year. So instead of repeatedly querying the FTP servers, we'll hit it one time for the entire country, compute a bunch of intermediate variables, convert those into efficient formats, and then we'll throw those back into the cloud in S3, right? That means that we can just handle the data for you. We know what 300 variables that you're going to use. We can make sure that they are available and streaming to your box without having to download anything. And you can sort of avoid the bloaty middleman of the federal government. I hate to put it like that. I worked at HUD in their GIS office. These are folks that care deeply about these data being used, but it's a lot of money to invest in new infrastructure. Okay, so instead of, this is hard to see, instead of downloading a shapefile for the entire country of every census tract in the country, which would take about 50 gigabytes in a shapefile from the census, here is every annual release of the 5-year American Community Survey with geometries, with about 500 socioeconomic and demographic variables, and they all come in, even the really highly detailed block groups come in at less than a gigabyte. Okay, you can read these directly from the S3 server without having to even download them. Okay, and that makes it really, really fast to get moving. Okay, the other problem that I mentioned is that these boundaries are incongruous, right? So the census has their own zoning system for blocks and tracts and block groups, and those don't nest perfectly with things like school attendance boundaries, right? The Department of Education doesn't necessarily care about the census's administrative boundaries that they tabulate to do their surveys in. So that's one problem if you want to combine multiple data sets. It's even a problem if you want to do temporal analysis for one data set, okay? So the census redraws its boundaries every 10 years when they do a new survey, right? Because of population growth and decline, it means the boundaries, which are designed to have like 4,000 people in them, need to be redrawn because people change where they live, right? But what that means if you're trying to do any sort of temporal analysis is you don't have a static unit. If I want to know what was say the median income of this tract in 1990 versus 2010, well, that tract doesn't exist in both time periods, right? So you have nothing to compare to. So here's a classic figure from Mike Reibel sort of to demonstrate that. And so the way that folks have solved this in the past is to just create data products. So this is the longitudinal tract database put together by some folks at Brown about 10 years ago. And what they did is look at what variables folks use, pick out the 200 census variables that everybody uses, and they converted everything into 2010 census boundaries. That way you can look and see what has changed between 1980 and 1990 and 2000 and 2010. And that's fantastic. There are hundreds, if not thousands, of studies that use this resource. It's wonderful. Now the problem is, you might want data or variables that are not available in the longitudinal tract database. You might need data for 2020, which isn't available from them yet. And you might want to put out a different geography, right? You might want, instead of converting everything to 2010 tracks, maybe you want a regular hex grid. Or maybe you want to convert everything to zip codes. Don't do that. Or maybe you want to convert everything into congressional districts and look at gerrymandering, or school districts to look at school segregation, what have you. Okay, and so what we decided was, instead of developing data products, like I just got through defending, we would need to build data tools that make it easier to do this process, so that folks can do this boundary harmonization on their own. So in GeoSnap, you can do that in basically one line. Okay, so I've got line 5 here just instantiates the data store. That lets me talk to all those data sets that I just described. Then I'm going to query that database, give me everything that you know about in San Diego County, so that's state 6, county 73 at the tract level. Now those come back with 1990, 2000, 2010, 2000, and 2010 in their original boundaries. So if we want to convert everything, say to 2020, all we need to do is specify in the harmonize function, convert everything to 2020. And that way we will be able to compare over time. Okay, I know you can't see these, but on the left, these are the original data in their original boundaries. And on the right, those are the same variables in higher resolution boundaries because of population growth in 2020. So the same data from these time periods, but represented as though they were in 2020 census tracts. And you can see that you get a little bit more variation closer to the coast. So here's what 1990 data looks like in 2020 boundaries. And here's what 1990 data looks like in its original 1990 boundaries, right? And so you lose those darker polygons near the coast. And that runs in less than a second. Okay, I didn't show you the code for this one. It really doesn't take any additional code other than to create the hex bins, but instead of passing a target year, you can pass a target geometry. And so now I have everything in a regular hex grid where one hex is exactly the same hex between two different time periods. And you get very different patterns depending on what your target is. Okay, so all the data munging aside, what about when we actually want to start analyzing neighborhoods and who resides in them and what they have access to? Okay, so the traditional way that you think about access and what people are able to consume in their neighborhood, the GIS way to do that is with a buffer. Right? You just take your point and say, this is where someone lives. If I think you walk roughly about 7 miles per hour, then I buffer you out 2 kilometers and say that's 20 minutes, right? That's this concept of like a 20-minute neighborhood. What do you have access to? Do you have childcare? Do you have jobs? Do you have health care inside 20 minutes? Okay, but urban spaces are not traversable like that, right? We can't fly. Instead, we have to navigate via networks. Okay, so because we are constrained to travel along networks, it means that if you do the traditional GIS buffer, you are probably overestimating exactly how far you can travel. So what this graphic does is compare the same time budget if you could fly versus if you were forced to walk. And then it compares these different networks because suburban development doesn't look the same as urban development. Chicago has this lovely regular grid so you can move everywhere. In suburban St. Louis, you get stuck in cul-de-sacs. Okay, and so if you don't account for that, you may be overestimating or underestimating. I think I saw Matt Davis in here, so this is using Pandana under the hood. We think this is really neat, in part because I know you can't see because of the title here, but the reason I have this slide here is to show you the wall time. Geosnap is not the only package that can do isochrones. You can call Mapbox or Valhalla or MapZen, all sorts of other folks, but you are forced to then interact with a service. You probably need an API key, and you're beholden to whoever creates that service and how their network works. You don't know how long it's going to take to get that computation back. Here is routing point to point and creating this polygon in under a second. That is ridiculously computationally intensive to calculate a shortest path between these different nodes. So to have these isochrones come back in less than a second, thanks to Pandana under the hood, I think this is really remarkable. Okay, so that's sort of one concept of a neighborhood, right? How far can you traverse? Another concept of the neighborhood that's very frequently used in in academia and in marketing in particular is this concept of geodemographics. Okay, and this is that product that I showed you earlier that Esri has, where they put a bunch of data into a cluster model, they create a typology of neighborhoods, and they sell it. Experian also has one of those products they call Mosaic. And basically what this is you take geographically referenced data, like from the census, stuff like race, class, ethnicity. You throw it into a cluster model and you map the results, right? You assign a type, a multivariate type to each geography and you map it. And here's what that looks like, okay? So here's Atlanta. If you throw, your sociological usual suspects, we call them, sort of race, class, home values, and throw it into a cluster model for Atlanta, here's what it looks like. I realize you can't tell a lot of what's going on here. You don't know what any of those colors mean, but what you can see is how starkly those spatial patterns emerge, right? Geography is not part of this analysis at all. It's just a cluster model and we're mapping it. So what this shows is how strongly Atlanta ends up in multivariate segregation is how I think of this, right? The fact that these neighborhoods all cluster together in space and all have similar attributes is giving us a sense that it's not just one dimension that leads to neighborhood sorting, it's race and class and ethnicity, and exactly the same thing that the Chicago school folks reminded us of in the 20s. Regionalization is a similar idea, except that it forces a contiguity constraint on it. Okay, so now we might ask, where are the neighborhoods? And instead of saying, well, this neighborhood up here is demographically similar to this neighborhood down here, and so they can both share a neighborhood type, type 5. This says, well, that's a neighborhood and this is a neighborhood, and because they are in different places, they cannot be the same neighborhood, obviously, even though they may share similar compositions. Okay, so Chicago has this on multiple scales. They have both neighborhoods and regions. So you can see how the neighborhoods then are grouped into larger regions. Again, GeoSnap, you can do this in basically one line. You feed it a cluster model, but it also understands how those observations are connected in space using a spatial weights matrix. And so you get a constrained clustering algorithm where you can only be grouped with similar observations that you are also contiguous with. Okay, and so this is a good way of looking at the multivariate segregation, but enforcing a contiguity constraint, right? This is like trying to recover the social areas that those sociologists were looking at 100 years ago. Okay, we also care about neighborhood change. Right now, we've just been looking at neighborhoods at a static point in time. Change matters quite a bit. I don't have to reiterate the specter of gentrification, but it's not just gentrification. The country is diversifying. It's not necessarily integrating. If you care about the geography of opportunity, it's a good idea to have a handle on where these things are moving. So I'm throwing this just to show you that the nice thing about GeoSnap is what it brings together. The data sets are all available to you. It can calculate 40 different segregation measures on the fly. It can do these geodemographic typologies on the fly, and that makes it really easy to wrap something like Streamlit around it to build yourself a nice little interface for exploring these trends over space and time. So this is a little income app that I cooked up maybe 2 years ago, and this took maybe an afternoon because I already have the engine prepared. So dropping a little decal on top is quite simple. Okay, we also might want to care about these multivariate transitions over time. So instead of just doing a single cluster model, I can look at how that cluster evolves at 4 different time periods. So this is 2013, 14, 15, and 16. What you see in these maps is that it's the colors, if I didn't put labels on these, you probably wouldn't know that these were 4 different maps, right? Because the colors are in almost the exact same spot. And what that's showing is that year to year, neighborhood change is not very common. Okay, if we actually look at that, the transition rates from how often does green stay green, how often does green become blue, how often does green become orange, and look at those rates, we can look at those as a heat map. So the origin type is on the columns here, destination type is on the row. That strong diagonal is exactly that intuition that we see here, that you tend to remain the same type year to year. So there is a 100% chance of green staying green. Now, the reason there are 7 heat maps on this slide is because we also might want to take into account space. So how often does green stay green? How often does green become orange? But how often does green become green when it's already surrounded by green? How often does green become orange once it's surrounded by orange, right? Because neighborhood change is conditional on context. If the neighborhood next to mine starts gentrifying, that might put pressures on my neighborhood because comparatively it looks very cheap, but they're almost in the same place, right? So making sure that we have an understanding on spatial context is what this is trying to get at. And once we know both the label and the context, it makes it very easy to draw a new label and simulate things into the future. So basically what this ends up being is a cellular automata on an irregular lattice where the transition rules are probabilistic. But this is a really simple way. This is created in about 4 lines of code from going from no data into a simulation model. And as I promised, I spoke too long and covered too much material. This is a graphic I cooked up 10 years ago, back when Twitter was still a thing. If you have questions, feel free to get in touch with me. Go Dutch.
You have about 5 minutes for questions. Again,
I'll indulge you quickly.
you have to answer them. So 5 minutes. Please repeat the question into the mic so that people.
Yeah.
How hard is it to integrate data, say, from like other countries, or?
Yeah, great question. So the data layer is agnostic to the rest of the package, right? We find ourselves using these data sets all the time, so we made the data layer available because we are American researchers who typically work here. Everything on the analytics side works everywhere else. So those isochrones, those are based on OpenStreetMap networks, right, anywhere in the globe. If you have, you're not limited to the data I showed you, either the American or necessarily those variables, right? If you've got local data from your planning department, integrate those as well. I have British colleagues that are using this in their research projects right now. Apologies, the question was, how well does this work for data outside of the country?
I'm very curious. What do you think is the kind of next steps? Or are there any missing pieces that you think you want to integrate?
Yeah, that is a really good question. So this has been sort of a personal enterprise for a while, right? So Serge and I and our group of folks over in San Diego have been working on this because we use these tools for our own research. I would love it if folks working in other countries would start building out the data resources like we've built for the US. Because this is not, I only ever have US examples to show, but that doesn't mean that this analysis is limited to the States. I also have Canadian colleagues working on this sorts of stuff and Dutch colleagues doing this sorts of stuff. So building out the data resources is one piece. And building out the simulations is another piece. So what we would like to do is start thinking about some scenario analysis. So all I did in that graphic was show you what happens if you take that model and run it forward. We also might like to say, well, what if you invest in this neighborhood, say, or, God forbid, what if the prices were to skyrocket in this neighborhood? What would happen to the layout? And so we can play with that by artificially changing those values and then let them run forward and see what happens. Right now you have to do that manually. There's not a good interface for doing that. And then finally, I think we will end up building a lot more sort of GUI level interfaces on top, right? The Streamlit folks and the visualization people who are all in town and are better at this than I am, have built really fantastic tools that make it like plug and play. And to have these sorts of data-based conversations with folks who can't write the code but want to use these measures in local planning departments or at the federal government, having those sorts of interfaces be the glue that sits in between these different audiences, I think is the next step.
Okay, I think that's all the time we have for questions, and someone has to get to a soccer game. Thank your speaker again.
Thanks, folks.